So here is a simple numerical, very simple numerical that we are going to solve, which relates all the concepts that we have learned so far. So our subscribers would know this already. So we are talking about the elastic potential energy of the spring. We are also talking about the Hooke's law, and we are also talking about the Young's modulus in this question. So all of those three concepts we have already studied. And here is the question. The question is asking us that if the stress remains the same, the strain remains the same, then the elastic potential energy of the spring is proportional to what? Okay, so is it proportional to length, cross-sectional, volume, Young's modulus? What is this proportional to? So what is strain? So strain is actually equal to delta L by L, where delta L is the change in length, L is the original length. Okay, that is the strain. Now what about the elastic potential energy? We know a formula for elastic potential energy, which goes as follows. So this is half K, where K is the spring constant, X square, X is our delta L here. So this is delta L squared. That is our potential energy formula. Now notice that in this potential energy formula, we don't have anything. We don't have length, we don't have cross section area, volume. So this question cannot be answered simply based on this formula. For that, we have to use another formula that we have studied, which relates our Young's modulus Y with our spring constant K. Okay, so that is the formula that we have already studied, and that is basically, it is K L by A. So that is our Young's modulus, relation between the Young's modulus and the spring constant K. So now that if we use this formula, we can make a small change to it. We can just say that we multiply both the top and bottom with the length, and this becomes KL squared divided by length into area. This is just volume. Okay, and no, why am I doing this? Why am I bringing volume into the picture? Because here there is a volume term here. So in order to understand the relationship between the volume, we have to bring volume from somewhere. So this is what I have done, and now we can say from here, what does this mean? This implies that my K is equal to Y, which is my Young's modulus, V by L squared. I substitute in this formula, and then I get half Y. Y is a constant, so I don't really have to worry about it. V is also there, so V we will just put, and then we have delta L by L, the whole squared. Now this delta L by L is nothing but our strain. So half Y V into strain squared. Now what the question is saying is that for same strain, which means that this is constant, it also means that as long as the strain is constant, my potential energy would change directly proportional to the volume. So this volume of course becomes the correct answer. Okay, so this is the first thing. Second thing is that if strain is constant, then my potential energy is also proportional to my Young's modulus. So this is also correct. Okay, so both of those C and D are actually the correct answer, and the trick here was to understand that using this, converting this K to the Young's modulus, I can get this L, and as soon as I have this L term here, I can now express this entire formula for potential energy in terms of strain. Okay, so that was the trick here. Okay, and of course this thing comes very naturally, right? As long as the strain is constant, the more the volume of the body for constant strain, the more the potential energy would be, right? It would be able to store the more amount of potential energy for the same amount of strain. That kind of somehow makes sense also, but we have just put that derived this in terms of a simple formula, and then we have just proved it, the answer to this question. Okay, so many such questions, practice many questions, they are available on DoorstepTutor.com. so they are just there. Just go ahead and practice, and I'm sure you will be successful in your exam. Thank you.